Columbia. He got his PhD at Princeton under Anatoly Spikowski. He was a Hubble Fellow. He was a Harvard ITC Fellow. He also has very strong opinions about pizza and Italian food, and has been known to smuggle large amounts of Parmesan cheese into the country at times. So he's an expert on all things collisionless plasma with simulations and across a wide variety of astrophysical environments, and he'll be talking about jets and accretion flows today. So,
am I in the line of sight for anyone? Because I moved this a little bit. I wanted to stay close. Is this better? All right. So thank you guys for being here. Thank you for having me here. Sean is checking that everything works okay for the Zoom. If not, let us know. I'm gonna say this now. Interrupt with questions at any time. Okay. So I think this is a learning experience for you, I hope. So let's try to make it such that nothing that I say, or at least as least as possible, what I say is obscure. Okay. So what I'm going to be presenting is some recent work that we have been doing in the direction of understanding the emission from black hole jets and coronae and the role of this process called magnetic reconnection, which I will be defining in case some of you are not incredibly familiar with it, for indeed powering emission from such systems. So what is reconnection? Slides. There you go. Oops. Okay. In the words of Russell Cousroot, maybe one of the pioneers of plasma astrophysics, at his 90th birthday party, Fermi told me to study reconnection 70 years ago. Here we are, and we still don't understand it. But apparently, Wikipedia knows what reconnection is. So reconnection is a process by which magnetic field lines of opposite polarity, oppositely oriented, get together in this green region where an intense electric current has to be there because the magnetic field reverses on a sufficiently small scales. And the magnetic field changes its integrity, its identity. You see the field lines advected left and right are now half red and half blue. Overall, the magnetic field geometry or topology has been changed on large macroscopic scales. This happens due to processes happening at very small microscopic scales localized in this sheet of intense electric current, that we will be understanding much more of in the next few slides. Very often, this is accompanied by an explosive energy release, and in fact, reconnection is often invoked whenever there are large episodes of dissipation and potentially very powerful and very fast evolving emission. Should I leave my camera on here? Or it doesn't matter? Okay. Maybe let me just kill it because the computer is computing. Okay, there you go. So reconnection is happening near us. This is an example taken from our own sun. The rearrangement of the magnetic field near the solar surface in the solar chromosphere and corona is responsible then for the coronal mass ejections on larger scales affecting the Earth as well and space weather on the Earth. Even closer to us, near the Earth magnetosphere, and this is a sketch, this is an artist's depiction, the interaction of the magnetized solar wind with the dipolar field of the Earth can cause reconnection on this side. It's called day side. You saw the snapping happening there. Another snapping is happening here. On the opposite side, it's called night side reconnection. So reconnection is happening near the Earth, near the sun. There is some peculiarity though of remote energetic astrophysical systems that near Earth environments do not have. And in particular, the difference between near Earth environments, lab, or really Earth magnetosphere-like situations, the important difference is quantified by this parameter, which I'm calling magnetization. This is the ratio, and it's going to be coming back over and over in this presentation. It's the ratio of the magnetic energy density, apart from a factor of 2, and the rest mass energy density of the particles. So this means immediately that if you are tapping this energy in the magnetic field into the particles. And if you are in a regime which is astrophysically irrelevant, in which the magnetization is much larger than unity, then your particles will immediately become relativistic. This is why this regime of reconnection is called magnetically dominated or relativistic. It's a statement, it's equivalent to a statement of the magnetic energy density is much larger than the rest mass energy density, or sigma, this magnetization, which will appear over and over again in my presentation, is much larger than unity. This is equivalent to stating that the Alfvén speed, the speed of hydromagnetic waves, is very close to the speed of light. These three statements are equivalent, and I will be working from now on in the regime of this high magnetization, which is a unique feature, an exciting feature of high energy astrophysical sources. A few more words of jargon. Let's come back to the Wikipedia page. In addition to the alternating magnetic fields that are going to be annihilating their energy, potentially into particle energy, reconnection setup often has a component that is sticking out or into the page, does not matter, but it's uniform, both on one side and on the other side, same direction, so it does not undergo dissipation. This component stays, it can change the dynamics of reconnection, but in general, its energy cannot be liberated into particle energy. The flow comes into this layer where the dissipation of magnetic field happens with a velocity that I'm calling Vn that is over 0.1 of the Alfvén speed. And for the case of high sigma reconnection, relevant for astrophysical high energy sources, Alfvén speed is the speed of light, so this inflow velocity is 0.1 of the speed of light. So the plasma and the magnetic field are being advected into this region with a speed as fast as 10% of the speed of light. We're often phrasing it in terms of reconnection rate, which is really a rate on which the magnetic field energy is being dissipated. So the statement about the inflow velocity being 0.1 of the speed of light is often phrased as the magnetic energy is being dissipated at a rate with a velocity that is over 0.1 of the speed of light. It's relatively fast. What happens to the energy? Some of the energy that the magnetic field liberates by dissipating can go into outflowing bulk motions. This is happening here on the left and on the right. You see this advection of the field lines that now are half blue and half red happening with a given velocity. That energy is ultimately resulting in sort of like a slingshot motion by the dissipation of the magnetic field. It's powered by the dissipation of the magnetic field. But even more interestingly and more importantly, some of the energy can be transferred to particles as heat, both in a thermal sense, this is a Maxwellian distribution in red, and in a non-thermal sense. So non-thermal particles, I'm defining them here, probably many of you are familiar with this jargon, are usually distributed in energy space in a power law fashion. So this is log of particle energy, this is log of how many particles you have. In log-log space, a straight line is what's called a power law, and generally non-thermal particles are distributed in a power law, with a power law distribution. Why reconnection can accelerate particles? We can kind of suspect why, but we'll get more quantitative about this later. As the flow comes into this reconnection region with this velocity Vn, the advection, just the advection of the magnetic field is bringing an electric field with it. This is the velocity equal to the E cross B velocity. So then the fact that the velocity at which the plasma comes in is over 0.1 of the Alfvén speed is equivalent to stating that the electric field is 0.1 of the magnetic field. So you have a 10% electric field nearly as strong, within 1 order of magnitude of the magnetic field, which is nearly as much as you can have. The large conductivity of astrophysical plasmas is usually enforcing the electric field to be less than the magnetic field. We'll see that in some cases this is not true. But generally speaking, the electric field should be less than the magnetic field. And in general, it's very hard for large regions to have a very large electric field. So reconnection can give you a macroscopic region everywhere here, in which the electric field is 10% of the magnetic field, which is nearly as much as you can have. I'm gonna pause for a second in case there are questions now, and then we'll get to the maybe more exciting, more interesting part. All right. I hope the movies are running fine here. They're a little bit, maybe we'll change. Yeah, go ahead.
Just a very basic question. So, is it generic that you expect the inflow velocity to be around 10% of the Albion speed, or is that very situation specific?
So whenever this parameter is much larger than unity, then that's the number to keep in mind. The statement, I think it is always the case that the inflow speed is 0.1 of the Alfvén speed. And then for sigma much larger than unity, the Alfvén speed is the speed of light, so the inflow speed is 0.1 of the speed of light.
And sorry, why is it?
Yeah, that's a good question.
Just mass momentum fluctuation.
The rate of inflow is not set by simple scaling laws, and in fact, MHD, which also satisfies mass momentum energy conservation, finds this rate to be 1 order of magnitude lower. This has been the subject of research for like 40 years, exactly why this number is 0.1. There have been quite a bit of progress in the last couple of years into understanding exactly how the details of the region around which reconnection happens, why their properties there are setting the inflow rate to be 0.1. I'm happy to share the references with you, but this question is far from being a trivial question.
Okay, cool.
All right, so how do we approach this problem? And the most fundamental way to, for some of you that were there this morning already, they've seen this sketch already, but the most fundamental way we can understand the physics of reconnection in this context is by using the particle in cell method. Sorry, I have one message on the chat. Explain why the reconnection rate is only 0.1. Yes, Taite. Yeah, so as I said before, 0.1 is a good number to keep in mind. For, I would say, 0.1 to 0.2 to 0.05, we're considering all of them to be over 0.1. And it's always 0.1 of the Alfvén speed. So if the Alfvén speed is much smaller than the speed of light, that 0.1 is still true, but related to the Alfvén speed. As I said, fundamental method, charged particles and electromagnetic fields, virtually not assuming anything. The particles are pushed with the Lorentz force. They are creating a current. The current is used in Maxwell's equations to solve for the electric and the magnetic fields. And the electric and magnetic fields are then used to push the particles around with the Lorentz force. And then you keep going. Now, this method is great because it really allows you to capture the fundamentals of the plasma physics. But on the other hand, typical scales, both length scales and time scales, are much smaller than astronomical scales. The typical length is listed here. It's the so-called plasma skin depth. It just depends on the density with a -1/2 power, and it's 10 to the 5 centimeters for a typical vanilla ISM density of 1 particle per cc. The characteristic time is over 10 to the -5 seconds, again for a characteristic density of 1 particles per cc. So you can see now how your astrophysical system of interest, which is varying maybe on parsec or kiloparsec scales, will have a huge scale separation between the global scales and the plasma scales that are listed here. So one needs, number one, very large simulations in order to say anything reliable at all. And two, to have physically motivated scalings and extrapolation that will go from the plasma scales all the way up to the astrophysical scales of relatives. Go back to reconnection. This is a vanilla simulation of reconnection done with the PIC method. The magnetization here is much larger than unity. In particular, it's 10 times more energy in the magnetic field than in the particles. And we'll see how it evolves. The magnetic field is initialized like this. So you see this anti-parallel configuration around the midplane, and we'll see how the evolution of the midplane looks like. The perturbation that we're imposing in the center will soon be forgotten, and all of the remainder of the movie will be self-consistently evolving. So these structures that we are calling plasmoids or flux ropes or magnetic islands are self-consistent density fluctuations, if you want, density structures that the reconnection process produces as a byproduct of its evolution. It's very dynamical, it's very hierarchical. The smaller scale grow first, and then they merge with each other, they transition to larger and larger scales, as you were seeing in the movie. So it's a hierarchical chain of flux ropes or plasmoids. However, you could do exactly the same thing in MHD and get a pretty similar picture. The rate, as I said before, changes, but the overall dynamics is not very different. So the reason why we're doing a peak simulation, most fundamentally, is to understand a little bit more the properties of the accelerated particles. So let's get to that part. Yes?
What sets the extent in the third dimension of the flux array?
Yeah, it's a good question. So it will run again, so we'll actually see what James means. So in a 2D plane, this will be the only plane that matters. This will be the y-x plane. The z direction is a peculiarity of 3D. And you'll see that the flux drops are actually not infinitely extended in that direction. This ultimately comes from a MHD-like instability that is called kink. So they are preferentially toroidal here, and an infinitely long toroidal field is unstable to a kink-like instability. This is what sets the length scale. So you would say that the length in the z direction is proportional to their cross-sectional radius, roughly speaking, within a factor of like 3 to 5. The system is going to be evolving differently if you have a guide field that's kind of enforcing the translational invariant along the z direction. So you'll see plasmoids more elongated along the z direction if you were to have a guide field than in this picture, which has a 0 or a very small guide field. So what can reconnection do for us? As I said, already bulk motions, some heat, some non-thermal acceleration, and then we'll get to the part that is more astrophysically related to applications. So non-thermal acceleration. And I'm going to be spending the next 10 minutes giving you my best summary of what we understand so far, what we understand as of today, about the physics of particle acceleration in relativistic reconnection. I'll be listing relevant papers. I'm happy to share the slides afterwards with people that have done most of the work for specific sections of my presentation. So the punchline is illustrated and summarized here. Reconnection naturally produces broken power laws. So power law, remember, it's a line in log-log space. This will be log of energy or particle Lorentz factor equivalently, log of number of particles. So if the number of particles differential in Lorentz factor is Lorentz factor or energy to the minus p, we call this slope of the power law p. At low energies, and I'll talk about this cut, this break afterwards, reconnection produces slopes that can be as hard as -1. So dn d gamma goes like gamma to the -1. We call this phase injection. The slope depends on the magnetization. That sigma parameter that quantifies the ratio of the magnetic energy to the plasma rest mass energy. At higher energies, kind of regardless, roughly regardless of the magnetization, the power law slope is -2. So the n over d gamma goes like gamma to the -2. What is this break? The break happens at a few times the magnetization. Now 3, it's a good number, but it's of order sigma, it scales with sigma. Now you should ask, how magnetized are the astrophysical systems I care about? What is this magnetization parameter? And usually for jets, it's like 10, maybe a little bit less, maybe a little bit more. However, there is an important point to remember that for electrons, the relevant break here is happening at 3 times the electron magnetization, which is defined as the ratio of the magnetic energy density to the rest mass energy density of electrons, which is smaller than the rest mass energy density of ions in the case of an electron-ion plasma. So the injection stage itself can bring electrons up to ultra-relativistic energies, 3 times the electron magnetization. In the case of an electron-ion plasma, it's related to the overall magnetization with this prefactor of almost 10 to the 4. So even if sigma, this sigma, is of order 1, which is not a very magnetically dominated system, but if the system is an electron-ion system, your electrons can be accelerated by reconnection in the injection stage already up to 10 to the 4, 10 to the 3, 10 to the 4 in Lorentz factor. Let's go to the first stage and we'll understand it a little bit more. So the punchline here is that ideal MHD cannot describe properly the injection stage. And I know some of you are actually working on this with Bart. In ideal MHD, the electric field can be written as minus V over C crossed with the magnetic field. And what we're finding, and I will be discussing and motivating it later, is that in reconnection, we find with PIC, that does not need to assume this, that the particles are interacting at first with non-ideal electric fields. And by that, I mean electric fields that cannot be written as minus B over C crossed with the magnetic field. Now, this condition can be declined in two different ways. For low guide fields, remember the guide field is the component sticking out of the page that does not go through dissipation. The electric field can be larger in some specific regions than the magnetic field. Clearly, if this is true, then the electric field cannot be written as minus B over C cross B for any velocity, right? In the case of strong guide fields, this condition is rather replaced by a statement about E parallel, meaning the component of the electric field that is parallel to the magnetic field. Again, if you take this equation, there is no component of the electric field that can be parallel to the magnetic field from this condition. So both these scenarios are scenarios in which the electric field is non-ideal, meaning it cannot be described within the context of ideal emission. So let me motivate why this is the right picture. This is a vanilla 2D simulation of reconnection. I will be showing 3 representative particles here. A bunch more are the small yellow dots. Magnetic energy in the top panel, in the bottom panel for those 3 particles, orange, red, and yellow. I'm following their Lorentz factor or energy as a function of time. And you'll see these 2 vertical lines. These are times in which the particle in question, the corresponding color, the particle in question is encountering a region where the electric field is larger than the magnetic field. So let's see how this goes. It's relatively smooth. So for the red particle, this is happening now. At the time that it crosses this middle region, the particle encounters an E larger than B region. Its energy shoots up by 2-3 orders of magnitude. It's kinetic energy. Similar story for the orange particle afterwards, later on, a time that is about now, when these 2 structures, these 2 magnetic islands are merging, they create actually another reconnection region in between, and the orange particle here is encountering, now this is exactly overlapping, it's encountering an E larger than B region. And once again, it gets a boost in energy, in this case by 1 order of magnitude. It will bring it to relativistic energies anyway. The yellow particle, on the other hand, never goes through E larger than B regions. That's why there is no dashed vertical line for it. And its energy stays relatively small. Lorentz factors of order just 1 of a few. So this overall picture of the importance of non-ideal fields for the early stages of reconnection, this is in some sense inevitable. That's where the particles need to be decoupled from the magnetic field. And it needs to be happening in regions that are special because of the presence of non-ideal fields.
So the suppressing effect of a guide field can be understood in terms of the incidence of E dot B.
The guide field has injection comparable. The slope of the injection is steeper, and that is controlled by processes that are occurring after this phase. So this phase will control whether the amount of energy per particle released by the injection stage is similar for guide field versus non-guide field. And that number is actually not very different between the 2 cases.
But in principle, you have a strong enough guide field that you just can't have E dot B.
If you do have a strong guide field, sorry, which one? This is
bigger than B.
Yes, this is a 0 guide field, and I'm using E larger than B condition.
Yeah.
For the strong guide field, it's E parallel, the only thing that matters. And somewhere in between, I think it's a little bit hard to say. Yeah. If you guys are overheating, maybe we can open some window. I don't know. I'm getting hot.
We're trapped.
We're trapped. Okay.
Let's open this.
Yes, go ahead.
I can just see that none of the particles disappear from the box, at least it doesn't look like it.
Yes.
A lot of other stuff is disappearing, so is that just waves, energy, what is going out of the box?
Yeah, this is a subsection of a larger domain.
I meant actually the top and the bottom.
Oh, right. So there is everything here is just inflowing.
Yeah.
So whenever a particle is trying to go back, it's going to be brought back by the V in that I had before. So there is E cross B speed that is pointing into the midplane.
And it's just waves going out?
Yes, these are actually fast magnetosonic waves. Yes. They're interesting for many reasons, but not directly for physics of the particle acceleration. Okay, so let's get to the second part. -2 sigma independent slope. What's the physics here? And here the answer is inevitably 3D. So what I showed before, the injection stage is roughly behaving the same way between 2D and 3D. Here, the dynamics for the post-injection phase is necessarily 3D. This is a 3D simulation. I'm showing the XY slice. This would be the equivalent of a 2D simulation with the magnetic field oriented like this. This is the ZY plane in which the magnetic field is getting out of the page and into the page. So you're looking at the other perpendicular plane perpendicular to the alternating fields. This is the trajectory of one particle. This will show it. This will be shown in the movie as well. So the particle is initially trapped into that plasmoid underneath here. You'll see it now. Yes, for a little bit, and then it breaks free. And it starts moving along the Z direction, going up and down the current sheet in this sort of like swimming freestyle motion. As it does so, it moves nearly along the direction of the electric field. The electric field here is out of the page, which means along Z direction. This is a positron. You have a positron whose orbit is exactly aligned with the electric field. There's nothing better than that in order to be efficiently accelerated. And in fact, if we measure the energization rate, it's electric field, charge, speed of light. Particle is roughly moving at the speed of light along the electric field. And since the electric field is 0.1 of the magnetic field, this is the rate at which the particle is being energized. And this happens because of 3D. The fact that the particle here is allowed to escape in the third direction, the Z direction, is because you're breaking the translational invariance along that Z direction by allowing your kinks, as James was asking before, to operate and break the plasmoids along that direction. This is one particle. It's happening for a whole lot of particles. Reconnection in 3D is a super efficient, super fast particle accelerator. The rate is listed here. This additional physics post-injection does not care about the non-ideal fields. So I made a strong point about the non-ideal fields earlier. Most of the work here is done by ideal fields. So it can be, I think, well reproduced by ideal MHD if the reconnection rate were to be the 0.1 speed of light reconnection rate. If you are now putting this into an astrophysical context, you can ask questions of whether reconnection can be a viable accelerator of ultra-high-energy cosmic rays. For typical jet parameters, for gamma-ray burst AGN jets, it turns out that it's possible. The proton seems to be getting a few times 10 to the 18 electron volt energies, which is putting them in the ultra-high-energy cosmic ray range. And iron in principle get to higher energy. I'm happy to spend more time on this, but I want here, and maybe this is good room for questions. So this is as much as I wanted to cover about the mechanics, if you want, of reconnection, how reconnection is able to dissipate the flow energy, the field energy, and put it into particle energy, potentially accelerating some of its particles to the highest ever energies achievable. So now let's talk about implications, especially for black hole jets and coronae. So this is a sketch that I got from Charles Gamy on the overall energy flow structure near a black hole accretion disk. So I looked at it and said, this is too complicated for me. So I asked my daughter to put some colors on it, and this is what she did. Now this starts to make sense. You have the accretion flow, you have a wind propagating away to higher latitudes from the accretion flow, you have the magnetospheric current sheet that Bart knows everything about. You have the jet, and you have a region in between the jet and the wind that I would say it's a jet-wind boundary. That's defined that. And reconnection can happen in multiple regions here, at least 3. The magnetospheric current sheet that is generated when you're piling up a lot of flux onto the black hole. You're getting to this MAD state, the magnetically arrested disk state. And the black hole is trying to expel the flux by erasing it through reconnection. There are two other occurrences of reconnection that I will be convincing you of. The boundary of the jet and the wind. This is a temperature plot from your own part. The jet boundary is brighter in temperature, hotter temperature. This is a signal that something is happening there from the point of view of dissipation. And I will try to give you the physical picture for why reconnection may be an integral part of the story there. And then I will discuss the role of reconnection in the context of the corona. I will be defining what the corona is or what we don't know about what the corona is. And I'm not adding any error because I don't know where the error would be. So let's talk about these two, jet wind boundary and then the corona. So reconnection at the jet boundary. And the observational motivation here is driven by this picture and similar pictures rather universally, I would say. Radio emission from relativistic jet is brighter on the outskirts than in the jet core. It's called limb brightening of the jet emission. So the obvious expectation is that there should be some dissipation channel activated at the boundary.
Why can't this be a Doppler effect?
That's a great question, actually. So
Because you expect the bulk motion to be slower in the boundary.
the bulk motion should be slower. I think the point that I am willing to buy onto is that if this were to be a signature that is geometrically rotated here, this is not enough to explain the fact that the core is slower. So let me rephrase it. So what I can say two things. If the jet emission is beamed away, then I agree with you. The jet outskirts can just have the same emissivity and just have slower Doppler boosting, so they will not be beamed away as much.
But we know, sorry, basic question, we know pretty well the orientation of the jet.
Yeah.
Really, don't we? And we know what the Lorentz factor is, I would think, from the
Well, the Lorentz factor itself is stratified.
superluminal motion.
Yes.
So what is gamma times theta?
Itself is bearing inside. Like the core of the jet usually go moving with a Lorentz factor of 10-ish. And then depending on the jet itself, you'll have a different direction along the plane of the sky. It's in general true that the jets that are observed in the radio band are not aligned with our line of sight. So you cannot assume that the jet boundaries are as Doppler boosted towards your line of sight as the jet core. And the jet core may be deboosted away.
So
I think that's a fair point.
So sorry for the basic question, but if gamma is varying across the jet, then the proper motion of radio blobs should vary across the jet as well. Is that a perceived?
Yeah, the blobs that are identified in the jet, I think, don't have a way to distinguish the boundary and the core. They're like
Or
this
they're
big.
two
Farther distances,
fuzzy.
they're very big. So I think we don't have a resolution to distinguish that. But the point on the Doppler effect, I think that's a valid point. In fact, you will see that as part of the evolution, the boundaries are actually moving slower necessarily than the jet core. The reason for looking at this, I think that the sort of like underlying reasoning is that there must be, or at least it's conceivable that there is, and that definitely the GRMHD simulations are showing hotter temperature at the jet boundaries than in the core, there is an energy channel for dissipation. You can even ask that question hypothetically, right? Is there some channel of dissipation that is acting at the boundary? And one potential source of free energy is the fact that the jet is moving faster than the surroundings. So whenever that happens, you would expect to have Kelvin-Helmholtz instabilities operating right there. These are pictures from our atmosphere. These are clouds that have a faster flow on top of them, or in this case, a slower flow. The same picture or the same physical scenario should be happening at the outskirts, at the boundaries of relativistic jets. And in fact, recent simulations are showing very rich dynamics of jet boundaries, including the presence of waves that are showing the same vortices that Kelvin-Helmholtz-like rolls are giving in our atmosphere. Now I'll stop this movie at a time. Yeah, unfortunately, I have some. You can see this here. You can see this one here as well, potentially this one as well. So the occurrence of this vortices seems to be a general expectation of what's happening at the boundaries of relativistic GRMHD jets. The key question is what this gives for the emission or the dissipation. So what is the nonlinear outcome of these waves? So we tried to oversimplify the problem a few years back. This is our jet in a pig box, in a kinetic description. It's not really a jet. There is no black hole here. The statement is just we want to study for conditions as realistic as possible the interface between a magnetically dominated region, which we envision the jet to be, and a plasma-dominated region, which we envision the outside material, ambient wind to be. This is an electron-ion plasma. This is an electron-positron plasma. This is moving. These are field lines, lines of magnetic field, not of velocity, but the velocity is also pointing up. And as I said, it's magnetically dominated in the sense that the magnetic energy per particle is larger than the resonance of the particle. Magnetic field is not just in the plane of the simulation, it's also tilted a little bit out of the page. So when this happens, Kelvin-Helmholtz does occur. So you'll see these vortices now growing at the two interfaces in very much the same way as you would expect for a natural evolution of the Kelvin-Helmholtz instability, which is an MHD instability. But we have checked that these are, which are kinetic results, have a growth rate that is in agreement with MHD expectation. Why that is important? Because we want to have large enough scales, even in our kinetic description, that we are still recovering MHD type dynamics. Because the jet boundary is an MHD scale shear layer. And the results are very encouraging. The linear growth rate matches very well MHD results. You can do this in resistive MHD and you get the same, not just linear evolution, but also non-linear evolution. At the end of the evolution, which is about now, you'll see that reconnection is an integral part of this story. Why? Initially, the magnetic field was just pointing up. But then, as a result of the Kelvin-Helmholtz, this produces vortices which are rotating the field lines back onto themselves. So initially, the field was just up, and now this, which comes from Kelvin-Helmholtz roll or vortex, has a component of the magnetic field pointing down. When this meshes onto this one, you have the perfect configuration for reconnection to happen. So reconnection is an integral part of the nonlinear outcome of basic MHD instabilities like the Kelvin-Helmholtz instability. At the end of the evolution, the boundary, this region where the dissipation has happened, has transrelativistic velocities, even though it was initially ultrarelativistic, and it has a plasma beta that is over 1. So the ratio of the gas pressure to magnetic pressure that initially was much less than 1 becomes 1 as a result of the dissipation. So in a sense, the intuition that Chris had before is what comes out as the nonlinear outcome of this evolution. What about particle acceleration? This is showing the same picture as before, together with the particle spectrum. So how many particles you have as a function, how many particles you have as a function of their energy or Lorentz factor. And you see that initially, all of the particles are rather cold. And then as the system evolved, and specifically once you get to the nonlinear stage of the Kelvin-Helmholtz, you develop a rather hard distribution extending to very high energies. This comes because of the reconnection process happening in the nonlinear stages of the Kelvin-Helmholtz. I'll maybe skip the next slide. This is a little bit more into the physics of the acceleration.
So
Yeah.
just a quick question about the acceleration.
Okay.
So you develop more energetic particles. When they leave the box, are they coming back in?
Yeah, this is a periodic box in the vertical
So
direction.
they experience a much longer.
They experience a much longer length scale. Yeah, so since Chris asked, let me spend a few more words on this. So this is an energy trajectory for one of the highest energy particles. The dashed red line is the work done by the parallel electric field parallel to the magnetic field. Remember from before when I talked about the injection stage, I argued that this component, electric field parallel to the magnetic field, is an integral part of what drives the injection, the first stages of energization for the particle. And this is still the case here. The first stage of energization is due to work by the parallel electric field. And at this point, the particle is on top of very intense current layers where reconnection is happening. So reconnection is really what's giving particles the first kick. And then the evolution later on, in this phase, you see the particle energy in a secular way goes up, even though there are oscillations. We attribute this to a process that is called shear-driven acceleration. This is basically the same way as Fermi acceleration at shocks. If you have a shock here, if you have a flow coming in and then the flow comes up, if a particle is trapped between the two sides of the shock, it will always see convergence or compression. And this is the way the particle energy increases. Here it's slightly different in the sense that you have flow velocity in this direction and the gradient is in this direction. So the gradient of the velocity is perpendicular to the velocity itself. In shocks, everything is aligned. But the same idea works if you have a particle here and it's bouncing off something moving towards you, it will gain energy, it will go to the other side, bouncing off something again towards it, it will gain energy again. This is what happens in the later stages. The particle can sample the velocity difference that you have across this shear layer and be energized by that after enjoying the injection by the reconnection in parallel.
So there's a trade-off.
You're not doing anything, right?
No, that's someone online. You can force your mute.
Oh. Well, let's see if it'd be okay.
Go ahead, Chris.
So there's a trade-off between efficiency and hardness of the spectrum.
Yeah. So the injection into the shear-driven part of the story, I think, is largely unexplored. You need to have enough energy to be able to sample your velocity difference. What that enough is, I think, is still very much unclear. The part of the story is the fact that itself, reconnection or the nonlinear evolution, by making all of this happen, is creating shear or even smaller scales than the initial scale of the shear. So the particle does not need to have necessarily post-injection alarm radius that is as big as the overall shear. You can sample small velocity differences on smaller scales, and then going up in energy, its alarm radius increases, it can sample a larger velocity difference. Shear-driven acceleration is a process that will get reinforced by additional energy gains. So whenever, if the energy increases, then it will become easier to be accelerated and so on and so forth.
I think you got to get rid of it.
Yeah, you still run.
Yeah, it's someone else. Yep.
Oh.
They messaged at their Bluetooth speaker and said,
Oh,
well, let's leave it, but if it happens again, we should.
Oh, I kicked them out already.
yeah.
Oh, okay. All right. So what are the implications? Particle acceleration via reconnection induced by the nonlinear stage of cardinal mode vortices can explain the limb brightening. Yes, dissipation is happening there, so it's likely a good explanation for that. The final stage presents a faster jet core that is often called spine and a slower surroundings that we call sheath. The jet is structured so with a faster spine and a slower sheath. This is assumed by Glaser models even before realizing that jets can be structured. So it nicely fits into those observationally motivated assumptions. And finally, and this is work that we have been doing recently with Jordi, these waves can actually be observable. This is a synthetic polarized image taken from one of the GRMHD simulations, showing that the imprint of such waves in the polarized signal, and specifically that the presence of these waves, of these vortices, tends to degrade the degree of polarization just because it's making things more messy, more turbulent as compared to the case of a laminar, non-wavy jet. So the lower polarization degree could potentially be an indication of the fact that such dynamics is indeed happening at the jet boundaries. With that, I will move to the last part, black hole X-ray coronae. What do we know about them? We know that the main motivation is coming from galactic sources, even though coronae are observed also in AGNs. In this case, I'm depicting, well, not me, but this is an artist's depiction of a black hole that is eating mass from a companion star, as in the case for X-ray binaries in our galaxy. They are observed in two different states. The soft state is thermal emission from the accretion disk. So what you learn in your classes about the Shakura-Sunyaev model should apply to the thermal emission here. In the hard state, instead, the emission shifts to higher frequencies, 1 keV, 100 keV, 100 keV for the hard state. And the usual interpretation is that some high energy coronal electrons are invoked to upscatter the disk photons to higher energies. Scattering is an inverse Compton process. You're having a fast electron here, releasing some of its energy to a soft photon and generating a harder photon. The usual interpretation is that you have such hot electrons somewhere energized by an unspecified process, such that the electron temperature is staying at about 100 keV. Optical depth inferred from coronal emission is of order 1, so you have a system that retains electrons at 100 keV with an optical depth of order 1. The key question is however, where this happens and whether the conditions are such that these 100 keV temperatures can be sustained. Right? We are relying here on the emission being powered by inverse Compton. Inverse Compton will be cooling the electrons, will be taking the electron energy away from them to give it into the photons. So is the electron able to be energized at a rate that is sufficiently fast to offset the cooling losses? And if you plug in realistic parameterization for your heating model, then the answer is no. The cooling time is so much shorter than the dynamical time, which is the typical time for replenishing the electron energy, that internal motions, the temperature of the electron should be significantly smaller than 100 keV. How come are we then just giving up and not explaining the hard X-ray emission? Reality is that these are not the only source of motions. Internal motions are not the only way motions can happen. You can have internal motions that are random, associated with temperature, and you can have bulk motions, in which in the comoving frame, the electrons will be cold, but they will be moving as a bulk. This is also an interesting and viable source of upscattering via Comptonization. What can power the bulk motions? That's the next question. I think you know the answer by now. Reconnection is surely a good candidate. Why? Because reconnection self-consistently produces these blobs, these packets, these islands, which are moving in a coherent way as a bulk. They contain a large number of electrons. The electrons may be cold in that frame, but this slingshot effect is producing bulk motions, and these bulk motions are a reasonable candidate, will be more quantitative in the next few slides, for Comptonizing the radiation. This is a relatively early on radiative peak simulation. The amount of cooling is quantified by this parameter, gamma critical or gamma rat. It's a Lorentz factor that is obtained by equating the accelerating power of the electric field to the Compton drag power. So it's the Lorentz factor at which the amount of energy that you can get out of reconnection balances the amount of energy that you're cooling due to inverse Compton. Higher Lorentz factors here, higher gamma critical, means necessarily a smaller photon field. So it's going towards the uncooled regime. Smaller values of this means a more pronounced photon energy density and a more pronounced cooling.
What mass ratio are you thinking?
This is 1. This is pairs. But I mean, we have done, as you know, like a series with electron ion, and I'll show you at the end the result for the X-ray spectrum with the electron ion case with mass ratio of 30, which is still not ideal, but it's getting to real. So the next 2 panels will show 2 quantities, and then you'll tell me whether they're different or not, or you'll think whether they're different or not. This is the total inverse Compton emissivity. So it's how much power you get from each cell, from each region of space, considering all the degrees of freedom of the particle motion, internal motions as well as bulk motions. In the bottom panel, we're getting rid artificially of the internal motion. So we're assuming that the electrons are moving only in response to the bulk motions, and we're computing the corresponding inverse Compton emissivity. So these two panels should be the same, roughly the same. This is a framework, this is a conclusion that states that the bulk motions are the key player in the Comptonization picture, and that internal motions are actually irrelevant for the strong cooling conditions expected in coronae.
Yes, please.
I know you want to grill me here. So this is a sketch of the picture we are envisioning. You have soft X-rays coming from maybe the disk, and then upscattering this coherent structures that the reconnection produces up to higher energies, harder X-ray photons, potentially 100 keV photons. And we can put this sketch on a more quantitative basis. This is the same simulation that I showed you before. This is particle energy spectrum, so how many particles you have as a function of their energy. The total spectrum is blue. The cyan is the spectrum accounting only for the particle bulk motions. So the fact that the peak of the cyan and the blue is nearly identical is a statement of the fact that internal motions, temperatures are not very important here. On the other hand, you can try to fit the cyan line with a Maxwellian. You shouldn't. Maxwellian is a signature of thermal motions. Here I'm just saying this is bulk. The cyan is just bulk motions. But the bulk motions have an effective temperature that is over 100 keV, which is exactly what we need for Comptonization models. So even though those 100 keV are not coming from temperature, the bulk motions in reconnection are naturally giving you this correct energy scale, the same energy scale that you would need for the observed Comptonized signal. Yes?
Just a naive question with your simulations from before. What determines if the plasmon goes left versus right?
The process is entirely stochastic. So for this one, we have outflow boundary conditions. Yeah. So we trigger things at the center to make sure that they're happily flowing out.
But in reality, you have many trigger sources and left and right. Like, will that change your picture at all?
So there can be an enhanced Comptonization if there are two regions that are fighting against each other, and you can have a photon that is traveling between the two. The regime here is kind of borderline because the optical depth is order 1, which means that you are allowed to go to the other side, but maybe not with 100% probability.
Okay.
So I think you can kind of see each of those as relatively isolated, but a final answer on this can only be tackled in a global sense. I think I could sell you one way, I could sell you the opposite way. If two reconnection layers are shooting at each other, I would say it's rather unlikely, but only a global system evolution will tell you whether that is the case. Yes.
I was just wondering, in your sketch, you had the magnetic fields coming out of the disk. I guess something like a bulbous Hawley type.
Yeah.
Is that internally consistent? Is too much to ask for, but is the sort of strength that you get roughly that you assume roughly right?
We'll get to that. I think
okay,
this is
right.
I'm going to show you a global picture that we're working on with Bart at the end, and then we can discuss more on that. But it's exactly, I think that's exactly what this will require. We have a candidate dissipation mechanism. This dissipation mechanism seems to be putting bulk motions on the right energy scale. Whether such reconnection layers are happening in a global evolution type of thing, that's exactly the question that we should be asking. Chris, you're
I utterly don't understand the basic claim, but let's leave it to the end of the talk.
All right. Happy to talk. All right, so I convinced you that the bulk spectrum can be approximated with a Maxwellian of order 100 keV. And if one were to trace photons through, the photons, this is an electron ion plasma now. So photons traced through our fixed simulations. The photon spectrum that we get out of it is the dashed or dotted lines for two different choices of that magnetization parameter, and the data points are the data points, and I think the case is there that the model fits the data relatively. So the final question that I would like to get to, can I still have 2 minutes or?
Yes.
Is where is the corona? So I'm gonna maybe downgrade this question a little bit to where is a corona, without the presumption to be giving you necessarily the picture of the corona you should be having in mind. The corona in some sense is like a unicorn, that we're trying now to have information about their properties, but exactly the overall shape and where this unicorn is sitting and what exactly the horn is and blah, 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 it's still a little bit uncertain. So the motivation for the next few slides is this simulation. Jiboy is part of this work, showing with radiative two-temperature GRMHT that if you start with a large-scale colloidal flux, you can have a thin disk in the outer region. This is the left panel here. You see the density here, relatively thin disk. And you have a thicker disk, MAD-like, magnetically arrested, in the innermost region of the accretion flow. So we're now not doing this simulation. We're just looking into the MAD-like region that is controlling the dynamics at the innermost scales. And we're trying to understand a little bit more about the properties of reconnection occurring there in a global sense. So this is work very much ongoing with Bart and a student of mine, Navin Sridhar. 2D simulations, GRMHT, high resolution, looking here at the plasma beta, the ratio of gas pressure to magnetic pressure. This is the magnetization, which I talked about already. And for your own interest, this is the magnetic flux threading the horizon. So you may be able to see evidence of of flux eruptions when the flux decays. The interest here is on the jet boundary, and I think what you should get out of this movie is just how active and how dynamic the physics of the jet boundary is. And you have reconnection plasmoids and reconnection structures at a number of times. Here you have this gigantic blob. I'm going to freeze the movie later on as well. You'll just realize how dynamic that boundary is and how universal and copious the presence of reconnection plasmoids is. The movie is looping back. I'm going to run it one more time. So looking at the jet boundary as a region that is filled with reconnection plasmoids is actually a tantalizing evidence. The GRM simulations are providing a tantalizing evidence for why this might be the case. And what we can do is to go one step further and say, okay, how do I actually define the jet boundary? And these two plots are giving you a sense that if you put a cut on the plasma beta and on the magnetization, these are the regions that will be colored, and these are the regions that from now on I'm going to call the jet boundary. So in order to produce significant Comptonized emission, we need, number one, enough power, and number two, enough or the proper energy scale. So this slide is convincing you that you have enough power. This is the radial electromagnetic flux measured as a function at one snapshot, as a function of the x and z or r and z coordinates. On the right, we're fixing one radius, 15 rg, and we're looking at the dependence on the polar angle. So 0 and pi here is the core of the jet. The brighter region here, more power carried, is exactly where the boundary is falling. So the jet boundary actually carries more power than the core of the jet, about twice as much, and an amount of power, electromagnetic power, that is roughly m dot c squared, so comparable to the overall accretion power, as needed for Cygnus X1. The second point that I promised you is about the energy scale. So let's go back to the movie that I showed before. This is the identification of the regions which we call jet boundary on a beta, plasma beta, and magnetization cut.
Stop yapping, I don't care.
And this is the bulk energy spectrum. They really want to listen to my talk. And this is the bulk energy spectrum for different radii. I'm almost done anyway. So the bottom line here is this is bulk, and yet it fits well with a 250 kV effective Maxwellian. So from a global simulation, by looking at the jet boundary, we have the right energy scale. The bulk motions there are exactly on top of what's needed for efficient comptonization to get the 100 kV peak observed for Cygnus X1. This is where we are so far. And we found this corona, and we found this unicorn. There are three things at least that are missing, now that we have at least one option for what the corona might be. Compute the self-consistent X-ray spectrum in a global sense, decide where the seed photons should be coming from. That's entirely a non-trivial issue. Polarize the emission as well. And now that we have these motions, I think it makes sense to think about timing signatures as well. The reverberation.
Well.
That has been, the reverberation that has been invoked and measured in a variety of sources, where does that come from? All right, with that I will stop. I'll leave you my summary, and I'm happy to answer any question, including from the Zoom user that is asking definitely good questions. All right, thank you all for having me. I'm around here, I'm around tomorrow. I'm happy to talk about any of the above. Now I kill the applause. You can do it again. I came here actually 5 years ago to talk about FRBs. So if you're interested about FRBs, I'm happy to talk about origin or propagation of FRBs. Any other plasma-related questions, I'm happy to chat about.
What were those like? It was like fountains, like in the movie of the jet. It was like periodic little fountains. Floors. Oh, that's all it is.
Oh, yeah.
Why is it like so?
In the core of the jet.
Yeah. Like
yeah.
the floors. I don't know, it just seems like very periodic.
What waves?
Yeah, this is right. This is all not believable.
I think it comes from the stagnation surface. The stuff moves away, and then you need to inject again, and then stuff moves away, and you need to inject.
Remove me all you want. I'm gonna keep joining.
Yeah, put them in the waiting room.
Sean, I think you can mute them.
Maybe we can just mute everyone and see if someone asks questions on the chat.
Like I think they can unmute themselves.
Every time he tries, you can force
Yeah.
you can force people to stay muted.
Even to stay?
Oh, no. Oh, there we go.
Exactly. Perfect.
So why is most of the power in the boundary layer? Maybe that's the question required as well.
Yeah, I think it's ultimately a question of how strong your toroidal field is, right? So this what we're measuring here is really E cross B, and the toroidal field, which is the one entering this calculation for the radial outflow, is just getting larger with larger distances from the core of the jet. And yet the plasma still moves at relatively large velocities.
Why is the toroidal field stronger? I mean, it may be related to the flow speed, I guess, but.
Yeah.
The rotation at the foot point anchor is a bit higher, I guess. Because the black hole rotates as a solid body, so it's rotating more rapidly toward the equator.
So we measured also the rotation, which was also larger, which was consistent
I
with
think the statement I can make is that right, we have derived this also just by assuming that the field lines are threading the horizon and moving, co-rotating with the black hole.
Yeah.
And a very similar profile that one we measured turns out here.
You're a special interest in Chinese intelligence, isn't it?
I think that's what I'm gathering, yeah. So as long as it is in the chat, it doesn't matter too much. Right?
But that's very interesting. So that's
Well, I mean, it's larger, but it's not larger by orders of magnitude, right? I think what I can say confidently is that it's larger by a factor of 2. And this is a case in which the jet has to be relatively strong. So, and it's also depending in some sense of what you're really calling a jet, right? So you might be calling a jet everything that moves with transrelativistic speeds. Everything that moves with transrelativistic speeds. I saw that. Okay. Transrelativistic speeds, and then you will be including both the jet core and the bounder, and then it's fine.
It was something that surprised us as well when we first saw it.
Yeah. So I think that
You're contagious, sorry.
well, the other point on the corona, I think that I'm sure you have in mind, is about the mass loading. So I think it is something that we are trying to
Well,
quantify.
no, I mean, the story about motion makes perfect sense for a mass ratio one. Okay.
Yeah, I think the question is whether you have enough
But
jet
if you
material.
have enough nonlinearity in the flow, you can transfer a good fraction of the flow energy to particles in the small scale and high magnetization as electrons.
Mhm.
Whereas the bulk flow, you're only tapping, it's like the ratio of,
Mass ratio, yes.
or the
Density
ratio
ratio.
of the compactness to the mass ratio, right?
So I think, we are now independently from this work trying to quantify better the composition in those regions that we call jet bounded.
Right.
And it's not obvious that the mass density is dominated by disk material. There is definitely some ion contribution there, but it's not obvious that the mass density is dominated by the disk. So it may be an electron-positron proton plasma in which the electron-positron mass density,
But then,
as much as we can trust
but
it,
then one would think, so the argument is that the positron loading should be pretty sensitive to the compactness, to the overall luminosity.
You would want to go straight to something
Yeah.
really.
Oh.
Yeah,
exactly.
What are they
maybe
doing?
we should just kill Zoom. We can ask Zoom people if they have questions, and that's it. We cannot kill the Zoom because
but in the waiting room is good.
That was a real comment.
That was a real
comment. Yeah, no, that's motivation.
Change the password.
Access. Password. We have a password.
Yeah, we have to change the password.
It's on the CITA website, so it's.
Is it on the snow website? Yeah. What?
The password should not be on there.
No, the password should not be
The
there.
password never on the website nor on the posters. It's way too
I'm sure this is something that we'll all remember, and next time I come here, we'll joke about it.
Or they'll return. Like,
Or
in 5
I'll
years
never
later.
come back here. You'll never want me back here.
Well,
So I think, yeah, go ahead.
Sorry. Okay, at the end, I'm gonna be honest, I did get a little lost, which is not your fault, obviously. But, so when you're talking about like what the corona is and where it is, are you saying it's in the boundary?
I'm saying that we are trying to understand whether this specific hypothesis makes observational sense.
A positive aspect of this is that you're getting rid of the disk, the cold disk. And so you don't have the black body bump.
The disk is truncated further out, which makes sense for Cygnus X1 because there is no evidence of a thermal component of the disk. Now, the same picture, you could say exactly the opposite for an AGN type corona, which shows a thermal bump very pronounced, and then probably either the disk is truncated not as far as for Cygnus X1, or it's not truncated at all, and this picture does not apply.
Actually, in Gilbert's simulations, we were looking at them last week, and even in the ones that are truncated, they're large cold blobs falling onto the black hole, which could potentially explain your iron line.
The broad
So it could even be an
And in fact, if you go back to this, right? If you were to say, oh, things are just super hot, this is actually, right? I think this is a photosphere. So I think the chance that the disk is actually screened by a large amount of the photon background. So I think this idea of like having cold regions in it is not great.
The large
But I think-
is a jet.
Yeah, I think one needs to, for the coronal emission, there are many there is a lot of observational information, which makes it very hard to think about one scenario that would work for everything. And I think, as far as I know, Bart will confirm, there has been not enough effort of understanding about the properties of the corona in a global sense, and see whether some ideas that have been proposed that just are merely based on geometry are actually making sense with everything we know so far about what the global dynamics of such systems is. So, maybe it will turn out that the corona is actually sitting above the disk and is due to differential rotation of foot points, of colloidal loops, threading the disks, opening up intermittently. Great. That could well happen. But has to be checked. We now have the beauty of this MAD regime, which seems to be occurring even in very luminous disks in the innermost regions, and inevitably creating dissipation regions mediated by reconnection at the jet boundary. Does this mean that this jet boundary is the picture that will work for all cases of the corona? No. This has been suggested actually without knowing much about without proving it with TRMHT as a good candidate for explaining the IXPE polarization. If we have some orientation, where it's not in the IXPE paper, but Jason Dexter said if you have an outflow and we're looking at the right angle and the outflow has some bulk Lorentz factor which are not very different than what we're getting here, then you can produce polarization degrees that are consistent with IXP. So I think there's a little bit of everything there. Did I confuse you more or?
I don't know what IXP is.
Oh.
And also, so like.
X-ray polarization explorer. So it's an experiment that measures the polarization in the X-ray band.
Oh, okay. So then I guess my next question is going to be if like this say X1 is the only like corona.
That's a good question. Yeah, no. So many X-ray binaries are seen with coronal emission. This is the best studied one. That's why everyone starts with this. Is all of the phenomenology that is seen here the same for all? No. They seem all to have similar properties of the spectrum, but as I said before, some of them are actually showing the persistence of this bump right here. And then you have this hard power law starting. So the hardness of the power law, the peak at 100 kV, plus or minus factor of few, I think these are generic attributes of coronal emission, but the degree of like soft versus hard, the polarization as well. I mean, IXP has two well-studied X-ray binary sources for polarization, and they seem to be completely different in what they're inferring about the properties of the corona.
So just a quick question though about the global energetics. So you were showing the Poynting flux.
Yeah.
But there's this big zone outside the boundary layer, which has lower Poynting flux.
This one.
Yeah. Well, at theta closer to pi/2, yeah. And so that really is the Poynting.
This is the disk actually getting in, and the Poynting flux here is not even positive.
Okay, but actually the Poynting flux isn't then a good measure of the dissipation necessarily.
Not here, no. I think for the jet boundary, I think it's good prospect.
So for the outflowing component, that's what you're measuring.
Yeah.
But the question is the total dissipation, especially in here, right? How does that compare with what's happening?
I think that's a good question.
Because ultimately that's what really matters for the radiation.
Yeah, I mean, I would say we don't see obvious, it could well be happening there and not being outflowing. I agree. Yeah. I think it's a good quantitative question.
Because there's probably a lot more mass there.
The density is larger. It's not obvious that the motions that you have there, in that case, it may be.
But there's gravitational energy being released as the stuff flows in,
Mm-hmm.
right? And that inevitably involves dissipation.
I think it's fair. The question that I'm making is whether the energy scale will be correct for getting 100 kV, and whether this is still in bulk motions or you'll need to rely on like a thermal comptonization model at that.
Right.
We don't see obvious evidence for let's say high gamma motions or like gamma where 1.5 motions at those latitudes.
I can believe that you've identified the dominant zone where bulk motions are, most important. But there's still this issue, you really have to fair load that layer, I think, to get this to work.
I think that's a fair point.
And, there's this big range of luminosities.
I think that's a very fair point. I think we are on the same page on this, and we are indeed now trying to quantify if not the pair loading, I would say the amount of ion sigma that you have there, or like how much ions are under dominant in masses compared to the pairs, and the pairs may be totally unrealistic because these are pairs from density floors. So, but at least the degree of the ion magnetization in those regions can be quantified. And then from there, I think you can do a calculation and understand what is pair loading that you would then expect. Yes?
What controls the going from the soft state to the hard state?
I cannot say. I'm as uninformed about this as everyone else.
Johannes, actually, do you have any idea? Sorry?
Lots of fish.
Yeah.
Empirically, what is it? Is it usually in the soft state or usually in the hard state?
The hard state is short.
Is that, oh,
Okay, was that a question? I'm not sure if everyone heard what you said, Chico. Maybe you want to speak up your reply earlier for what controls the transition.
I was saying maybe flux leakage or expulsion of flux, magnetic flux in the system.
But it needs to be something that is beyond what a single simulation can do, right? Because we are starting here with a given initial condition, or the idea is to get to a steady state with that initial condition. And then if the feeding is different, if the accretion is different, if the flow is differently magnetized.
Even if you were able to, based on some initial condition, if you could get some straight transition, even the timescales are impossible to simulate a full cycle.
Exactly, it's very long.
Does this only work when there's a black hole that's the that object?
It's a great question. I would say no. If the accreting neutron star will have a jet boundary, I think the jet boundary in accreting neutron star will have the same physics as the jet boundary here. You mean observationally? There is, yes. Yes. Yeah. I mean, at least within this picture, right? Within a picture in which the jet boundary is doing the quantization, the same thing should work. Actually, it's even more obvious that you will have a jet in that case. To be rotating, definitely rotating.
Have you looked for any quasi-periodicity in your boundary? Okay, that's good.
Not yet.
I see.
Are you worried at all? Because you said one side of the boundary has a whole bunch of numerical artifacts that you don't trust so much, but it is still part of the picture for setting the structure on the boundary layer.
I can reproduce, I guess we are in a good stage to understand that if the dynamics is sufficiently force-free, that sigma is sufficiently large, whether this should be even larger or not, from the point of view of the overall dynamics should not matter.
Okay.
But it's definitely a question that many people in the MHD, GRMHD community have in mind to do a better job.
I think there are two additional comments. One is, for example, pointing flux. You need E and B, right? And in principle, those don't suffer from flaws. That's a good thing, right? Yeah. And pointing flux is roughly the only thing you can trust from the jet. The other thing is,
that's the reason why you can't trust everything else, is because that dominates.
Yeah,
exactly. The other thing is the temperature that you get in this boundary layer may at times, definitely during or shortly after flux eruptions, be set by material that is pushed from the black hole into the boundary. And that material is heated up to a temperature proportional to the sigma in the jet. But sigma in the jet is completely artificial. It's order of magnitudes below what it is in reality. So the temperature in that boundary layer may be or is affected by numerical arguments, so like 100%.
But I think, maybe I can jump in, I think this is exactly the reason for why we are using this framework of bulk quantization, right? The bulk velocity of the jet boundary is set by E cross B velocity. So as much as you trust the electric and magnetic fields there, you trust the bulk motions that you have there. And that's much more reliable at that point as a source of quantization, other than a thermal quantization model,
Yeah.
which, as Bart was saying, the temperature will be set by how much density you have actually injected
Yes.
artificially in your MHD.
Yes, but I'm sure the instabilities.
They
that you're
may be
developing here
different.
may
They
still
may be
affected.
different. I think that's to be checked, and we are checking it in a periodic, well-controlled experiment. MHD with various degrees of magnetization, peak potentially with various degrees to very large infinite magnetization. Peak doesn't worry about magnetization of 10 to the 6 being an issue. And then we can see where the development of these surface instabilities is different. But I think my confidence is that if you have a sigma that is sufficiently high on the jet side to be nearly force-free, then it doesn't really matter whether you have sigma 100 or sigma 100,000.
Keep in mind that the alphane speed is the square root over sigma of sigma over sigma plus 1. So whether you're at 10 or 100 or 1,000, for the alphane speed doesn't matter. It's the speed of light. So that is one argument to be made. Sigma above a certain number doesn't matter for the dynamics.
But it may be that the mixing is controlled by exactly the mass densities. And then
Yeah, exactly, this is what I was thinking.
Then I think it's a good question. No more questions on Zoom?
Drawings.
Songs. I hope there's like, we get some kind of more insight to this. I don't know.
I just saw that the Zoom link went out on Twitter.
All right.
And I don't know how.
With the password?
I don't know how protected that Zoom link was.
Honestly,
Was that sorry from CITA?
yeah, with the password on it.
I don't know. All I can see is the like a small URL for the Zoom
And the
link.
Zoom link is public, the password shouldn't be.
Yeah.
Sometimes random email addresses write to us asking for
Yeah.
information.
Well, I think this means we have to change the Zoom password.
Yeah.
To something more secure.
Yeah.
Or is there like a sting operation? We can have like a fake seminar and then like track them.
Do a fake
I'm
seminar.
happy to
with
talk
it.
about other things and see whether they're still interested.